Division of segments and angles, Level 1. In the following series of videos, we will learn how to identify midpoints, bisectors of segments, trisection points, trisectors of segments, adjacent angles, angle bisectors, and angle trisectors. We will start this video series with midpoints and bisectors of segments. In geometry, we often work with segments that are divided in half. A point or segment, ray, line, or plane that divides a segment into two congruent segments bisects the segment. Bi is a prefix that means two, and sect means to cut. In this sense, the bisector is a thing doing the cutting. The bisection point is called the midpoint of the segment. The midpoint represents the middle of the line segment. This point is exactly halfway between both endpoints. It is important to note that only segments can have midpoints. It does not make sense to say that a ray or a line has a midpoint. Remember that segments are measurable and have a definite length. Rays and lines have an indefinite length. Recall that rays extend infinitely in one direction, and lines extend infinitely in two directions, so they have no midpoint. Midpoints are defined for segments only. For example, the midpoint of segment PQ is represented by point M. Point M is said to bisect segment PQ. This means that point M divides segment PQ into two congruent segments. We can conclude that the length of segment PM is equal to the length of segment MQ. In other words, segment PM is congruent to segment MQ. A point is not the only figure that can bisect a segment. In fact, another segment, ray, line, or plane can also bisect a segment. For example, in the following figure, segment XY bisects segment AC at point B. We can conclude that point B is the midpoint of segment AC and that segment AB is congruent to segment BC. In this figure, point D is the midpoint of segment FE. We can conclude that segment FD is congruent to segment DE, because point D bisects segment FE. We can also conclude that ray DG bisects segment FE. In the next figure, segment OK is congruent to segment KP. We can conclude that point K is the midpoint of segment OP. We can also conclude that line JM is a bisector of segment OP, since it is collinear with the midpoint K. As a final example, in the following diagram, plane X bisects segment AB at its midpoint P. You can think of this plane as slicing segment AB at point P, creating two congruent segments, in this case, segment AP and segment PB. So a point, segment, ray, line, or plane can bisect a line segment, creating a midpoint which divides the segment in half, creating two congruent segments. Next, let's talk about trisection points and trisectors of segments. A segment divided into three congruent parts is said to be trisected. Tri is a prefix that means three. Two points or segments, rays, lines, or planes that divide a segment into three congruent segments trisect the segment. The 2 points where the segment is divided are called the trisection points of the segment. Recall that midpoints are associated with segments. In the same manner, trisection points is also associated with segments. This means that rays and lines do not have trisection points. In the following figure, segment AR is congruent to segment RS, which is congruent to segment SC. From this information, we can conclude that point R and point S or trisection points of segment AC. This means that segment AC is trisected by points R and S. In the next figure, if point E and point F are trisection points of segment DG, then we can conclude that segment DE is congruent to segment EF, which is congruent to segment FG. We can also conclude that segment HE and HF are trisectors of segment DG, since these figures cut segment DG into 3 congruent segments. Alright, before we talk about angle bisectors, let's quickly talk about adjacent angles. Adjacent angles are 2 angles in a plane that have a common vertex and a common side, but no common interior points. For example, in the diagram shown, angle 1 and angle 2 are adjacent angles. The next diagrams illustrate examples of non-adjacent angles. Notice that angle 3 and angle 4 are not adjacent angles. When we describe adjacent angles, we are picturing diagrams like the ones on the left. Alright, now let's talk about angle bisectors. An angle, like a segment, can be bisected. A ray that divides an angle into 2 congruent adjacent angles bisects the angle. The dividing ray is called the bisector of the angle. In the following figure, the measurement of angle ABD is equal to the measurement of angle DBC. In other words, angle ABD is congruent to angle DBC. From this information, we can conclude that ray BD is the bisector of angle ABC. As an additional example, if angle NOP is congruent to angle POR and ray OQ bisects angle POR, then we can conclude that ray OP is a bisector of angle NOR. We can also conclude that angle 1 is congruent to angle 2. Alright, let's end the video by going over angle trisectors. 2 rays can divide an angle into 3 equal parts. 2 rays that divide an angle into 3 congruent adjacent angles trisect the angle. The 2 dividing rays are called trisectors of the angle. In the following figure, angle ABC is congruent to angle CBD, which is congruent to angle DBE. From this information, we can conclude that ray BC and ray BD trisect angle ABE. As a final example, if ray SV and ray SX are trisectors of angle TSY, then we can conclude that angle TSV is congruent to angle VSX, which is also congruent to angle XSY. Alright, so to recap, segments and angles can be divided. The special ways to divide segments include segment bisectors and segment trisectors. Segment bisectors intersect a segment at a point called the midpoint, dividing the segment into 2 congruent segments. Segment trisectors intersect a segment, creating 2 points called trisection points, which divide the segment into 3 congruent segments. The special ways to divide angles include angle bisectors and angle trisectors. Angle bisectors divide an angle into 2 congruent adjacent angles. Angle trisectors divide an angle into 3 congruent adjacent angles. Alright, in our next video, we will start applying these new concepts and go over some basic examples. Division of segments and angles, Level 2. In this video, we will apply the concepts learned from the previous video to solve basic problems related with division of segments and angles. Let's go ahead and start with the first example. In the following diagram, segment RS is congruent to segment ST. Can we conclude that point S is the midpoint of segment RT? In this problem, we are provided with a figure and are asked to determine if a point is a midpoint of a segment. Recall that a midpoint of a segment divides a segment into two congruent segments. At first glance, this seems to be the case since we are given that segment RS is congruent to segment ST. Unfortunately, point S is not the midpoint of segment RT. In order for a point to be considered a midpoint, it has to be collinear with the endpoints of the segment. Looking at the diagram, we see that point R, point S, and point T are not collinear, so point S cannot be a midpoint. This is an example of a special case where two segments that share the same point are congruent, and yet the common point between the segments is not a midpoint. Alright, let's try the next example. In the following diagram, ray BD bisects angle ABC. Can we conclude that ray DB bisects angle ADC? In this problem, we are provided with a figure and are asked to determine if a ray bisects an angle. We're given that ray BD bisects angle ABC. This means that ray BD will split angle ABC into two congruent angles. In this case, angle ABD is congruent to angle CBD. Now, just because it looks like ray DB is a bisector of angle ADC does not mean that it is. We cannot assume this from the diagram. We need to determine this with the given information. Notice that segment AD, DC, CB, and BA may or may not be the same length. We have no way of determining this, so the angle may or may not be bisected by ray DB. So in the end, we do not have enough information to reach that conclusion. Okay, let's take a look at the next example. In the following diagram, point B and point C trisect segment AD. Can we conclude that ray EB and ray EC trisect angle AED? In this problem, we are provided with a figure and are asked to determine if two rays trisect an angle. We are given that point B and point C trisect segment AD. In other words, segment AB is congruent to segment BC, which is congruent to segment CD. Notice that it is true that segment AB is congruent to both segment BC and CD, but the fact that segment AD has been trisected does not mean that angle AED has also been trisected. We would need more information to draw a decisive conclusion. So no, we cannot conclude that ray EB and ray EC trisect angle AED. Now let's take a look at some proof examples. Given that ray PS bisects angle RPO, prove that angle RPS is congruent to angle OPS. In this problem, we are provided with some geometric relations and a diagram. We are asked to show or prove that two angles are congruent. We're going to use a two-column proof to show that these two angles are congruent. Let's start by marking the diagram with the given information. In this case, we are given that ray PS bisects angle RPO. This means that angle RPS will be congruent to angle OPS. So let's mark these two angles with single arc marks. Now that we have a labeled diagram, let's go ahead and prove the conjecture. We will start with the given information. In this case, ray PS bisects angle RPO, and the reason is because it is given. With this statement, we can conclude that angle RPS is congruent to angle OPS, and the reason is because if a ray bisects an angle, it divides the angle into two congruent angles. This is essentially the definition of an angle bisector, and this ends the proof. Alright, let's try the next proof. Given that line CM bisects segment AB, prove that segment AM is congruent to segment MB. In this problem, we are provided with a conjecture and a diagram. We are asked to prove that two line segments are congruent. We're going to once again use a two-column proof to show that these two line segments are congruent. Let's start by marking the diagram with the given information. In this case, we are given that line CM bisects segment AB. So we are going to draw a single tick mark on line segment AM and line segment MB. Now let's proceed with the proof. For our first statement, we will write line segment CM bisects segment AB, and the reason is because it is given. Now we can conclude that segment AM is congruent to segment MB, because if a line bisects a segment, it divides the segment into two congruent segments. This is essentially the definition of a segment bisector, and this ends the proof. Let's move along to the final example. Given that segment DH is congruent to segment HF, prove that point H is the midpoint of segment DF. In this problem, we are provided with a geometric relation along with a diagram. We are asked to prove that a point is a midpoint of a line segment. Similar to the previous examples, let's first mark the diagram with the given information. We are given that segment DH is congruent to segment HF, so we draw a single tick mark on each of these two segments in the diagram. Next, we will use a two-column proof to show that point H is the midpoint of segment DF. We will start with the given information. In this case, segment DH is congruent to segment HF, and the reason is because it is given. From here, we can conclude that point H is the midpoint of segment DF, because if a point divides a segment into two congruent segments, then it is the midpoint of the segment. This is essentially the definition of a midpoint, and this ends the proof. Alright, in our next video, we will go over more basic examples involving division of segments. Division of segments and angles, Level 3. In this video, we will go over more basic examples involving division of segments. Let's take a look at the first example. Name the congruent segments. Point O is the midpoint of segment CD. In this problem, we are asked to determine which segments are congruent given that point O is the midpoint of segment CD. Recall that a midpoint splits a segment into two congruent segments. Since point O is the midpoint of segment CD, it will split it into two congruent segments. We can illustrate this by drawing a single tick mark for segment DO and segment OC. In this case, segment DO is congruent to segment OC. And this is our final answer. Alright, let's try the next example. Name the congruent segments. Segment SW bisects segment XV. In this problem, we are also asked to determine which segments are congruent given that segment SW bisects segment XV. Since segment SW bisects segment XV, we know that segment XV will be split into two congruent segments. We can illustrate this in the diagram by drawing a single tick mark for segment XW and segment WV. In this case, segment XW is congruent to segment WV. And this is our final answer. Alright, let's take a look at the next example. Point B and point C trisect segment AD. Find the coordinates of point B and point C, and the measurement of segment AC. In this problem, we are provided with a diagram of a line segment with 4 points. We are given that point B and point C trisect segment AD, This means that these 2 points will split line segment AD into 3 congruent segments. In this case, line segment AB will be congruent to line segment BC, which is congruent to line segment CD. So we can draw a single tick mark for each of these line segments. Since all 3 line segments are congruent, all we need to know now is the length of segment AD. We can determine this length by using the coordinates of point A and point D. In this case, the length of segment AD is equal to the absolute difference between the coordinates of point D and point A, which is equal to 21. Now that we know the length of segment AD, we go ahead and divide this length by 3 to obtain the length of each congruent line segment. In this case, each line segment will have a length of 7. With this length, we can now determine the coordinate of point B and point C. The coordinate of point B will be equal to -5 plus 7, which is equal to 2. And the coordinate of point C will be equal to 2 plus 7, which is equal to 9. Finally, we can determine the measurement of segment AC by finding the absolute difference between the coordinates of point C and point A, which simplifies to 14. And this is our final answer. Alright, let's move along to the next example. In the diagram, line segment HL and line KT intersect at the midpoint of line segment HL. Classify each statement as true or false. Segment LM is congruent to segment MH. In this problem, we are provided with a diagram, along with some geometric relations. We are asked to determine if the following statement is true or false. Before we attempt to answer this question, let's mark the diagram with the given geometric relations. We are given that line segment HL and line KT intersect at the midpoint of line segment HL. This means that line segment HM and line segment ML are congruent, since a midpoint splits a line segment into 2 congruent line segments. So let's go ahead and draw a single tick mark for each line segment. Now let's determine if the statement is true or false. The statement reads segment LM is congruent to segment MH. Looking at the diagram, we see that segment HM and segment LM are indeed congruent. So we can conclude that this statement is true. Let's take a look at the next statement. Segment MT bisects segment LH. Notice that the endpoints of segment MT are collinear with line KT. Since we are given that line KT intersects at the midpoint of segment HL, we know that line KT is a bisector of segment HL. The endpoints of segment MT are collinear with line KT. We can conclude that segment MT is also a bisector of segment HL. So this is a true statement. Alright, let's move along to the next example. Name the following: the midpoint of segment BF. In this problem, we are provided with a diagram of a number line, along with some points located at a particular coordinate. We are asked to determine the midpoint of segment BF. Let's first determine where segment BF is located in the number line. We know that point B is located at -2, and point F is located at 2. In order to determine the midpoint, we need to know the length of this line segment. We can determine the length by taking the absolute difference of the point's coordinates. In this case, the length of segment BF is equal to 4. We know that the midpoint will be located at a distance that is half this length, relative to either endpoint of line segment BF. If we start at point B and move 2 units to the right, we end up at point D with a coordinate of 0. Notice that point D is 2 units away from both point B and point F, so we can conclude that point D is the midpoint of segment BF. Okay, let's take a look at the next example. Draw segment CD and segment RS so that the conditions are satisfied. Segment CD and segment RS intersect, but neither segment bisects the other. In this problem, we are asked to draw a diagram so that the given conditions are satisfied. The condition states that segment CD and segment RS intersect, but neither segment bisects the other. Let's start by drawing segment CD. Next, we need to draw segment RS intersecting segment CD, making sure that this intersection does not bisect either of these two line segments. We can show this by not drawing any tick marks in the diagram. So the following diagram is one of many possible drawings that satisfy the conditions. Let's take a look at the next condition. Segment CD and segment RS bisect each other. Similar to the previous problem, we can illustrate these conditions by drawing two line segments that intersect very close to each other's midpoint as follows. Then, we need to draw tick marks for each line segment to show that each line segment is bisected. So we draw single tick marks for one line segment and double tick marks for the other line segment, as follows. So this diagram is one of many possible drawings that satisfy the conditions. Let's take a look at the final example. Segment CD bisects segment RS, but segment RS does not bisect segment CD. Just like the previous two problems, let's draw two line segments, making sure that segment CD intersects segment RS around its midpoint, as follows. We also need to make sure that the midpoint of segment RS is not the midpoint of segment CD. We can illustrate this by drawing single tick marks on segment RS, as follows, making sure we do not add any tick marks on segment CD. So this diagram is one of many possible drawings that satisfy the conditions. Alright, in our next video, we will go over more challenging examples involving midpoints, bisectors, and trisectors. Division of segments and angles, Level 4. In this video, we will go over more challenging examples involving midpoints, bisectors, and trisectors. Let's go ahead and jump straight into the first example. In the diagram, point X is the midpoint of segment VZ. The length of segment VW equals 5, and the length of segment VY equals 20. Find the coordinates of point W, X, and Y. In this problem, we are provided with a diagram of a number line, with points located at particular coordinates along with the measurement of two line segments. We are asked to determine the coordinates of 3 of these points. Alright, let's start the problem by marking the diagram with the given information. We know that point X is the midpoint of segment VZ. This means that segment VX and segment XZ are congruent, so the segment's lengths are also equal to one another. We also know that the length of segment VW is equal to 5, and the length of segment VY is equal to 20. With this information, we can determine the coordinates of each of these 3 points. For point W, we know that its coordinate is going to be 5 units to the right of point V, which has a coordinate of -12. Moving 5 units to the right from -12, we land on -7. In a similar fashion, the coordinate of point Y is going to be 20 units to the right of point V. In this case, point Y will have a coordinate of 8. Lastly, the coordinate of point X can be determined by finding the length of segment VZ and taking half this length. To find the length of segment VZ, we can compute the absolute difference of the segment's endpoint coordinates. Doing that, we obtain 34. we now take half this length, which is equal to 17, and use it to find the coordinates of point x by moving either 17 units to the right of point V or 17 units to the left of point Z. Doing that, we obtain 5 for the coordinates of point x, and this is our final answer. Alright, let's take a look at the next example. Segment EH is divided by point F and point G in the ratio 5:3:2 from left to right. If the length of segment EH is 30, find the length of segment FG and name the midpoint of segment EH. In this problem, we are provided with a line segment that is divided into 3 smaller segments. We are given the length of one of these segments, as well as a ratio of the lengths between these 3 segments. We are asked to determine the length of one of the segments and identify the midpoint of the largest segment. For this type of problem, we're going to make use of the geometric relations that are provided to us and use them to set up an algebraic relation. We know from the problem that the length of the 3 segments are in the ratio of 5:3:2. Since we do not know the actual length of each of the segments, we are going to use a variable and let the length of segment EF be equal to 5x, the length of segment FG equal to 3x, and the length of segment GH equal to 2x. This way, the algebraic expressions are consistent with the ratios given to us. Next, we notice that point E, F, G, and H are collinear. This means that the length of segment EF plus the length of segment FG plus the length of segment GH will be equal to the length of segment EH. Using this geometric relation, we can go ahead and substitute the algebraic expressions for the length of each segment as follows. Now it is just a matter of solving for x, so we collect like terms and divide both sides of the equation by 10. Doing that, we obtain x equals 3. With this value of x, we can now determine the length of each line segment. In this case, line segment EF is equal to 15. Line segment FG is equal to 9, and line segment GH is equal to 6. Notice that line segment EF has the same length as segment FH. They are both equal to 15. This means that point F is the midpoint of segment EH, since it divides segment EH into 2 congruent segments, and this is our final answer. Alright, let's try the next example. Given that the length of segment OM is equal to x plus 8, the length of segment MP is equal to 2x minus 6, and the length of segment OP is equal to 44. Determine if point M is the midpoint of segment OP. In this problem, we are provided with a diagram of a line segment along with some algebraic and numerical expressions, which represent the lengths of 2 smaller line segments. We are asked to determine if a point represents the midpoint of a line segment. In order to determine if point M is the midpoint of line segment OP, we are going to use the definition of a midpoint, along with the algebraic and numerical expressions provided in the problem. We know that the length of segment OP is equal to 44, so if point M is the midpoint of line segment OP, then it will bisect the segment into 2 congruent segments, each measuring half of 44. In this case, each one will measure 22. We can use this length and set it equal to the algebraic expressions representing segment OM and MP. We will then solve for x for each equation. If we happen to get the same solution for both equations, then we can conclude that point M is the midpoint of line segment OP. If we get a different solution for each equation, then we can conclude that point M is not the midpoint of line segment OP. So solving for x on each equation, we obtain x equals 14 for the first equation and x equals 14 for the second equation. This means that point M is the midpoint of line segment OP, since the same value of x satisfies both equations. And this is our final answer. Alright, let's take a look at the next example. Point B and point C are trisection points of segment AD, and the measurement of segment AD equals 12. Find the length of segment AB and segment AC. In this problem, we are provided with a diagram, the measurement of a line segment, and the fact that 2 points are trisection points of a line segment. We are asked to determine the length of 2 smaller line segments. We are first going to label the diagram with all the given information. In this case, the length of segment AD is equal to 12. We will also mark segment AB, segment BC, and segment CD with single tick marks, since point B and point C are trisection points of segment AD. Recall that trisection points split a line segment into 3 congruent segments. Now that we have labeled the diagram, we can go ahead and start solving for the length of segment AB and segment AC. We know that the length of segment AD is equal to 12. We also know that segment AD is split into 3 congruent segments. Each of the congruent segments has a measurement equal to 12 divided by 3, which is equal to 4. This is also the measurement of segment AB. The measurement of segment AC will be equal to twice the measurement of segment AB. In this case, it will be equal to 8. And this is our final answer. Let's end the video with a final example. If the length of segment AB is equal to x plus 3, and the length of segment AE is equal to 3x plus 6, find the length of segment AE. In this problem, we are provided with algebraic expressions representing the lengths of 2 distinct line segments. We are asked to find the length of one of these segments. From the previous example, we know that segment AB measures 4, so we can equate this value with the variable expression x plus 3. This will allow us to solve for the unknown variable x. Doing that, we obtain x equals 1. Now that we know the value of x, we can go ahead and substitute it into the algebraic expression representing the length of segment AE. Substituting this value for x and simplifying, we obtain 9 for the measurement of segment AE. And this is our final answer. Alright, in our next video, we will continue going over more challenging examples involving midpoints and segment bisectors. Division of segments and angles, Level 5. In this video, we will go over more challenging examples involving midpoints and segment bisectors. Let's take a look at the first example. Point E is the midpoint of segment DF. Find the value of x if the measurement of segment DE equals 2x minus 3 and the measurement of segment EF equals 5x minus 24. In this problem, we are provided with a graph of 2 line segments intersecting at a common point. We are given algebraic expressions for the lengths of 2 line segments. We are asked to find the value of x. Let's start by marking the diagram with the given information. We know that point E is the midpoint of segment DF. This means that segment DE and segment EF are congruent, so we mark these 2 segments with a single tick mark. We also know that the length of segment DE equals 2x minus 3, and the length of segment EF equals 5x minus 24. Since we know that both segment DE and segment EF are congruent, we can go ahead and set these 2 algebraic expressions equal to one another. Now we have an equation for which we can solve for x. So we subtract 2x from both sides of the equation. Then we add 24 to both sides of the equation. Lastly, we divide both sides of the equation by 3. Simplifying the expression, we obtain x equals 7 as the final answer. Alright, let's take a look at the next example. Given that line TP bisects segment VS and segment MR, segment VM is congruent to segment SR, the length of segment MP is equal to 9, the length of segment VT is equal to 6, the perimeter of figure MRSV is equal to 62, find the length of segment VM. In this problem, we are provided with a diagram of a figure, along with various geometric relations. We are asked to find the length of a particular segment. We will start solving this problem by marking the diagram with all the given information. This will help plan our approach in solving this problem. We know that line TP bisects segment VS and segment MR, so we can go ahead and draw single tick marks on segment VT and segment TS, and double tick marks on segment MP and segment PR, since these two pairs of segments are congruent to one another. In addition, we are also given that segment VM is congruent to segment SR, so we will use triple tick marks to illustrate this on the diagram. Next, we go ahead and label the measurement of segment MP and label the measurement of segment VT. In this case, they are equal to 9 and 6 respectively. Lastly, we can write a geometric expression for the perimeter of the figure. In this case, segment VM plus segment MR plus segment RS plus segment SV is equal to 62. Now let's figure out how we can determine the length of segment VM. We will start by assigning a variable to our unknown length. So let's label the length of segment VM with the variable x. Since segment SR is congruent to segment VM, we can also label this length with the variable x. We also know that the length of segment PR is equal to 9, since it is congruent to segment MP. Similarly, we also know that the length of segment TS is equal to 6, since it is congruent to segment VT. Now we can take all of these measurements and substitute them into our perimeter expression. So we replace the length of segment VM and segment SR with x, and replace the length of segment VS and MR with 12 and 18 respectively. Now it is just a matter of solving for x, so we collect like terms, subtract the constant, and divide both sides of the equation by 2. Doing that, and simplifying, we obtain x equals 16. Since this value of x also represents the length of segment VM, we are essentially done with the problem, so this is our final answer. Alright, let's end the video with a final example. Given the diagram, find the value of x. Determine if point Q is the midpoint of segment PR. In this problem, we are provided with a diagram of a line segment broken into two smaller line segments. We are also given the measurement of line segment PR and algebraic expressions representing the measurement of the smaller line segments. We are asked to determine the value of x and determine if point Q is a midpoint of segment PR. Let's start by determining the value of x. Notice that we have expressions for the measurement of all three line segments. We also know from the diagram that point P, Q, and R are collinear. This also allows us to set up the following geometric relation. The length of segment PQ plus the length of segment QR is equal to the length of segment PR. We can now substitute the algebraic and numerical expressions into this geometric relation. Doing that, we obtain the following equation. From here, it is just a matter of solving for x. Notice that we are face to face with a quadratic equation. So let's move every single term to one side of the equation so that we can set the equation equal to 0, making sure we add like terms along the way. We also want to write the quadratic equation in standard form. Next, we need to see if this quadratic expression is factorable. So we use the factors of the constant term, in this case 4 and -2, and use them to set up two binomials. In this case, the quantity x plus 4 times the quantity x minus 2. Having factored the quadratic expression, we go ahead and use the zero product property and set each factor equal to 0. We then solve for x for each factor, Doing that, we obtain x equals -4 and x equals +2. Now we need to figure out if we can use both of these solutions. We can figure this out by substituting each value of x into the algebraic expression representing the two smaller line segments. If we obtain positive measurements, then we will know that it is a solution to the problem. If we obtain negative measurements, we need to eliminate the value of x, since measurements must be positive and not negative. Let's first substitute -4 into each algebraic expression and simplify. Notice that the measurement of segment QR ends up being negative, so we have to discard -4 as a potential solution. Now let's substitute +2 into each algebraic expression and simplify. In this case, we obtain positive measurements, so let's use this value of x to finish the problem. We need to determine if point Q is the midpoint of segment PR. This will be the case if the measurement of segment PQ is equal to the measurement of segment QR. Looking at the measurements for each segment when x equals +2, we conclude that point Q is not the midpoint of segment PR, since both measurements are not equal. And this is our final answer. Alright, in our next video, we will go over examples that involve adjacent angles, angle bisectors, and angle trisectors. Division of segments and angles, Level 6. In this video, we will start going over examples that involve adjacent angles, angle bisectors, and angle trisectors. Let's start by going over the first example. Name all angles adjacent to angle 6. In this problem, we are provided with a diagram and are asked to name all the angles adjacent to angle 6. Recall that adjacent angles have a common vertex and a common side, but no common interior points. In the diagram, we see that angle 6 has point D as its vertex, so any adjacent angles will also have this point as a vertex. In this case, angle 7 and angle 5 fit this description, so angle 7 and angle 5 are adjacent to angle 6, and this is our final answer. Let's take a look at the next example. Name 4 angles that are adjacent to angle FOG. Similar to the previous problem, we are provided with a diagram with various angles and are asked to name 4 angles that are adjacent to a particular angle. Let's first identify angle FOG in the diagram. Notice that angle FOG has point O as its vertex. This means that any adjacent angles will also have this point as its vertex. One such angle would be angle HOG. Another angle would be angle FOC. A third angle would be angle FOB, and a fourth angle would be angle FOA. All of these angles have angle O as a vertex and share a common side to angle FOG. So this is our final answer. Let's move along to the next example. Given that ray KO bisects angle JKM and angle JKM is equal to 41 degrees 37 minutes, find the measurement of angle OKM. In this problem, we are provided with a diagram, along with a geometric relation and the measurement of an angle. We are asked to find the measurement of an angle. Let's start solving the problem by first labeling the diagram with the given information. We know that ray KO bisects angle JKM. This means that angle JKO and angle OKM are congruent, so we draw single arc marks for each angle. We are also given that the measurement of angle JKM is equal to 41 degrees 37 minutes. With this information, we now know that the measurement of angle OKM is just half the measurement of angle JKM. So we go ahead and divide the measurement of angle JKM by 2. We can divide this angle by 2 in a couple of ways. We can go ahead and rewrite this angle in decimal form, and then divide it by 2. or we can divide the degrees and minutes by 2, as follows. Now it is just a matter of simplifying this angle. Notice that we have 20.5 degrees and 18.5 minutes. Let's rewrite the half degree into 30 minutes and add it to 18.5 minutes. We now have 20 degrees, 48.5 minutes. The last step is to convert half a minute into seconds. So let's rewrite half a minute into 30 seconds. In the end, the measurement of angle OKM is equal to 20 degrees, 48 minutes, 30 seconds. And this is our final answer. Alright, let's take a look at the next example. Name the congruent angles. Ray RO bisects angle NRP. In this problem, we are asked to name the congruent angles given that ray RO bisects angle NRP. Recall that an angle bisector will split an angle into two congruent angles. Since ray RO bisects angle NRP, it will split it into two congruent angles. In this case, angle NRO is congruent to angle PRO. And this is our final answer. Alright, let's try the next example. Name the congruent angles. Ray XT and ray XV trisect angle SXW. Similar to the previous problem, we are asked to determine which angles are congruent given that ray XT and ray XV trisect angle SXW. Recall that angle trisectors split an angle into three congruent angles. In this case, angle SXT is congruent to angle TXV, which is also congruent to angle VXW. And this is our final answer. Okay, let's take a look at the next example. Name the angle bisector. In this problem, we are asked to determine the angle bisector. Looking at the diagram, we see that angle FJG and angle HJG have matching arc marks. This means that these two angles are congruent. Notice that ray JG divides these two angles. This means that ray JG is the angle bisector of these two angles. And this is our final answer. Alright, let's move along to the next example. Name the angle bisector. The measure of angle POK is equal to the measure of angle MOK. In this problem, we are provided with a diagram and are asked to determine the angle bisector given that the measurement of angle POK is equal to the measurement of angle MOK. Recall that if two angles have the same measurement, then they are congruent. We can show this on the diagram by drawing single arc marks for each of the angles, as follows. Now it is just a matter of naming the ray that bisects these two angles. In this case, it is ray OK, and this is our final answer. Let's take a look at the next example. Find angle XTZ if ray TZ bisects angle XTY, and angle XTY equals 60 degrees. Here we are provided with a diagram and are asked to find angle XTZ given that ray TZ bisects angle XTY, and angle XTY is equal to 60 degrees. Since ray TZ bisects angle XTY, we know that angle XTZ and angle YTZ are congruent, so we can draw single arc marks for each of these angles. We also know that angle XTY is equal to 60 degrees. Since an angle bisector splits these two angles equally, we know that the measure of angle XTZ is going to be half the measure of angle XTY. In this case, the measure of angle XTZ is equal to 30 degrees. And this is our final answer. Alright, let's end the video with a final example. Given the diagram, what ray bisects which two angles? In this problem, we are provided with a diagram with various angle measurements. We are asked to determine an angle bisector and name the angles that are bisected. To solve this problem, we need to find two angles that are congruent and share the same ray as one of its sides. Since this figure represents a protractor, we know that it measures 180 degrees. Notice that angle HOA is a straight angle and is bisected by ray OC, since it splits this straight angle into two congruent right angles. Also notice that angle COB and angle COG are congruent since they both measure 70 degrees. These angles also share ray OC as one of its sides. This means that ray OC is also an angle bisector of angle GOB. In the end, ray OC is the angle bisector of angle HOA and angle GOB, and this is our final answer. In our next video, we will go over more challenging examples involving angle bisectors and angle trisectors. Division of segments and angles, Level 7. In this video, we will go over slightly more challenging examples involving angle bisectors and angle trisectors. Let's take a look at the first example. Given that the measurement of angle FGJ is equal to 3x minus 5, the measurement of angle JGH is equal to x plus 27, and ray GJ bisects angle FGH. Find the measurement of angle FGJ. In this problem, we are provided with a diagram, along with algebraic expressions representing the measurement of two angles. We are also given that a ray bisects an angle. We are asked to find the measurement of a particular angle. Let's start by marking the diagram with the given information. We know that the measurement of angle FGJ is equal to 3x minus 5, and that the measurement of angle JGH is equal to x plus 27. We also know that ray GJ bisects angle FGH. So let's draw single arc marks for angle FGJ and angle JGH, since they are congruent. Now that we have the given information labeled in the diagram, let's go ahead and plan how we are going to solve for x. We know that angle FGJ and angle JGH are congruent. We also have an algebraic expression representing the measurement of both of these angles in terms of x. So let's go ahead and set both of these algebraic expressions equal to each other. Now we can solve for x. So we first subtract x from both sides of the equation. We then add 5 to both sides of the equation. Finally, we divide both sides of the equation by 2 and simplify. Doing that, we obtain x equals 16. The last step is to use this value of x and substitute it into the algebraic expression representing the measurement of angle FGJ. Doing that and simplifying, we obtain 43 degrees for the final answer. Alright, let's take a look at the next example. Given that angle ABC is equal to 90 degrees, angle 1 is equal to 2x plus 10, angle 2 is equal to x plus 20, and angle 3 is equal to 3x, determine if angle ABC has been trisected. In this problem, we are provided with a diagram and the measurement of 3 distinct angles. We are asked to determine if a particular angle has been trisected. In order to determine if angle ABC has been trisected, we need to show that angle 1, angle 2, and angle 3 are congruent. Before we do that, we need to figure out the value of x so that we can use it to determine the measurement of each angle. Notice that angle ABC is a right angle, since it measures 90 degrees. So we can label angle ABC with a small square mark. We also know from the diagram that angle ABC is formed by angle 1, angle 2, and angle 3. This allows us to set up the following geometric relation. The measurement of angle 1 plus the measurement of angle 2 plus the measurement of angle 3 is equal to the measurement of angle ABC. With this geometric relation, we can go ahead and substitute the algebraic and numerical expressions for each angle. Doing that, we obtain the following equation. From here, we can solve for x. Let's first collect like terms. Then we subtract 30 from both sides of the equation. We then divide both sides of the equation by 6. Simplifying the expressions, we obtain 10 for the value of x. Now that we know the value of x, we go ahead and substitute it into the algebraic expressions of angle 1, angle 2, and angle 3. Simplifying the expression for each angle, we obtain 30 for all three angle measurements. Since all three angles are congruent, we can conclude that angle ABC has been trisected, and this is our final answer. Let's end the video with a final example. Ray OG and ray OH divide straight angle FOJ into three angles whose measures are in the ratio 4:3:2. Find the measurement of angle FOG. In this problem, we are provided with a diagram of a straight angle that is divided into three smaller angles. We are asked to find the measurement of one of these smaller angles. In order to figure this out, we need to determine the value of x, so that we can substitute it into the algebraic expression of angle FOG. We can figure out the value of x by setting up an equation using a relevant geometric relation. We know that angle FOJ is a straight angle. This means that it measures 180 degrees. We also know that angle FOJ is divided into three smaller angles, so we can set up the following geometric relation. The measurement of angle FOG plus the measurement of angle GOH plus the measurement of angle HOJ is equal to the measurement of angle FOJ. Notice that we are given an algebraic expression for the measurement of the smaller angles. These measurements are in the ratio of 4:3:2. We also know that the measurement of angle FOJ is equal to 180 degrees since it is a straight angle. With this equation, we can now solve for x. So we collect like terms and divide both sides of the equation by 9. Simplifying the expression, we obtain 20 for the value of x. Now that we know the value of x, we can go ahead and substitute it into the algebraic expression representing the measurement of angle FOG. Simplifying the expression, we obtain 80 degrees as the final answer. Alright, in our final video on this series, we're going to go over two challenging examples involving angle bisectors and angle trisectors. Division of segments and angles, Level 8. In this final video on division of segments and angles, we will go over two challenging examples involving angle bisectors and angle trisectors. Let's jump straight into the first example. Given that ray OP and ray OR trisect angle NOS, the measurement of angle NOP equals 3x minus 4y, the measurement of angle POR equals x minus y, and the measurement of angle ROS equals y minus 10, find the measurement of angle ROS. In this problem, we are provided with a diagram, along with a geometric relation and algebraic expressions for the measurement of three angles, in terms of x and y. We are asked to find the measurement of a particular angle. Let's start the problem by labeling the diagram with the given information. We know that ray OP and ray OR trisect angle NOS. This means that angle NOP, angle POR, and angle ROS are all congruent to one another. So let's draw a single arc mark for each of these angles. We are also given an algebraic expression in terms of x and y for these same angles, so let's mark them in the diagram. Now we need to figure out a way to find the value of x and y in order to determine the measurement of angle ROS. We know that the three smaller angles are congruent to each other. This means that we can set up the following geometric relation. The measurement of angle NOP is equal to the measurement of angle POR, which is also equal to the measurement of angle ROS. From this geometric relation, we can set up three distinct equations. The first equation is the measurement of angle NOP is equal to the measurement of angle POR. The second equation is the measurement of angle POR is equal to the measurement of angle ROS. And the third equation is the measurement of angle NOP is equal to the measurement of angle ROS. For this particular problem, we only need two equations to solve the system of equations in two variables, since we have two unknowns, in this case, x and y. So let's use the first two equations and substitute the corresponding algebraic expressions for each angle. Next, we notice that the algebraic expression for angle ROS only contains the variable y. So we only need to determine the value of this variable, and we do not need to know the value of the variable x. With this in mind, let's go ahead and solve for x in the first equation. Solving for x in the first equation, we obtain the following. We now do the same for the second equation and solve for x. Doing that, we obtain the following. Now we can go ahead and substitute one of these two equations into the other. Let's substitute the first equation into the second equation. Now let's get rid of the fraction by multiplying the entire equation by the value in the denominator. From here, it is just a matter of solving for y. Doing that, we obtain y equals 20. Now we can determine the measurement of angle ROS. Substituting the value of y into the algebraic expression for the measurement of the angle, we obtain 10 degrees, and this is our final answer. Alright, let's end the video series with a final example. Angle BAC is equal to 120 degrees, and points D, E, and F are in the interior of angle BAC, as shown. Ray AD bisects angle BAF. Ray AE bisects angle CAF. Find the measurement of angle DAE. In this problem, we are provided with a diagram, along with the measurement of an angle, in a couple of geometric relations between rays and angles. We are asked to find the measurement of a particular angle. Let's start solving the problem by labeling the diagram with the given information. We know that angle BAC is equal to 120 degrees. We also know that ray AD bisects angle BAF. This means that angle BAD and angle DAF are congruent. So let's mark these two angles with a single arc mark. We are also given that ray AE bisects angle CAF. This means that angle FAE is congruent to angle EAC. So let's mark these two angles with double arc marks. Alright, now let's figure out a way to determine the measurement of angle DAE. At first glance, it seems that we are missing some information, and this problem is impossible to solve. Before we come to that conclusion, let's determine all the geometric relations that we know from the given information. We know that angle BAC has to equal the sum of the smaller angles, in this case, angle BAD, angle DAF, angle FAE, and angle EAC. We also know that angle BAD is congruent to angle DAF. Let's represent the measurement of these two angles with the variable x. In the same manner, angle FAE is congruent to angle EAC. Let's represent the measurement of these two angles with the variable y. We can now substitute these variables and the measurement of angle BAC into the geometric relation representing the sum of all the angles to obtain the following expression. Now we can add like terms to simplify the equation. Notice that we have an expression in terms of two variables, x and y. It seems that we need another equation in terms of x and y to solve the system of equations. Before we try to generate another equation, let's find an expression for the measurement of angle DAE in terms of x and y. Notice that angle DAE is equal to the sum of angle DAF and angle FAE, or in terms of our variables, it is equal to x plus y. So if we can figure out what x plus y is equal to, we can determine the measurement of this angle. Notice that if we take the geometric relation representing the sum of the angles and divide it by 2, we obtain the following expression. And jackpot, we now know the value of x plus y. In this case, it is equal to 60 degrees. And this is our final answer. Alright, and this wraps up the division of segments and angles video series. In our next video series, we will go over the basics of coordinate geometry.